Hi, this is Dr. Memari, and I am going to perform the experiment 2, which is kinetic for 1046 lab taking at Central campus. One more time, the purpose of me performing the experiment is for you to be able to watch the video later and record the data in order to complete your data sheet and turn in your data sheet as an assignment to your professor. If your professor is me or someone else is going to hold a mini lecture on Blackboard Collaborate or different way of explaining the theory of the experiment more in depth, and make sure that everything is clear to students. So if you have any questions, you could ask your professor. Again, if it's me or someone else, you ask your professor about your questions that you might have about calculations or other questions you might have from the experiment. So we're going to look at the theory of the experiment. First, what is kinetic? Kinetic is basically a study of the reaction, the rate of the reaction, how fast this reaction is taking place. Speed of the reaction, I'm sorry, speed of the reaction, it depends to different factors. One is temperature, the other one is concentration. And concentration of reactant. The reactant can't affect the rate of the reaction in different order. Sometimes it's a direct one-to-one. That means if you double the concentration, the rate is going to double. If you triple the concentration, the rate is going to be tripled, and that means the rate of the reaction is first order with respect to that specific reactant. A zero order means that, what does zero order means? It means if you change the concentration of that specific reactant, rate is not going to change. So that means zero order reaction. A second order reaction means that if you change the concentration, the rate is going to change, but what ratio is going to change? If you change the concentration, you double the concentration of one of the reactant and the rate is quadrupled, that means the rate with respect to that specific reactant is a second order. So how do they measure the rate? Basically, the time that it takes for reaction to happen, based on changing concentration of the reactant or changing concentration of the product. So if the concentration of the reactant changes over the time, using the balance equation, you can calculate these the rate for the reaction. A general rate for this reaction is given by this equation number 6. Rate equals K, concentration of A to the power of X, concentration of B to the power of Y. A and B are reactants. X and Y are the values that are determined experimentally. So basically, you have to do 2 or 3 experiments and change concentration for A, for example. For trial 1 and 2 in this table, you're changing concentration for A from 1 mole to 2 moles, but concentration of B stays constant. Then you would say rate for trial 2 over rate for trial 1 equals the other side of you divide the equation. K concentration for trial 2 times concentration trial 1, and values for B and Y is going to cancel. So when you divide the rate for trial 2 by rate by trial 1, the B is going to cancel if you're using trial 1 and 2. And then is going to be, then you are going to take trial 1 and 3, where concentration for B has changed, concentration for A is the same, and this way you can calculate the value for Y. So you can calculate A to the power of X. That would be the order of reactant A, and then the power of Y, it shows the order for rate with respect to reactant B. If you have the value for X and Y, then you can calculate the value for K, which is the rate constant. If you have the rate, you have the values for X and Y, you have concentration for A and B, you have the value for K, you can calculate rate. If you have the rate, or so any variable that is missing, you should be able to calculate after you have a rate law for your reaction. So if you have rate law for reaction, that means you already have the value for X and you have value for Y. Concentration for A and B is going to be known to you because you are making that concentration for a specific reaction. If the rate has been measured by the time, measuring the time, then you can calculate the value for K. If K is given, then you can calculate for rate. The concentration or change in temperature can affect also the value for rate. So at different temperatures, if you find the rate, you can find the K at different temperatures. So temperature 1, 2, and 3 is going to have rate value 1, 2, and 3. As a result, if your concentration stays the same, the value for K can be calculated. So you calculate the value for K at temperature 1, 2, and 3. If you have the temperature, you in Kelvin, and you have the K value at different temperatures, you can plot the graph of L and K versus 1 over T in Kelvin. Then you have a graph. If it's not perfect line, you are going to find the best fitted line. And when you have the best fitted line, you can calculate the slope, which is rise over run. The delta, you take any 2 points of the graph, you find the y2 minus y1, or the values for y divided by values for x, or rise over run, and then you get the value for slope. The value for slope is the EA over R. EA over R. EA is activation energy and R is a constant number. So since you have these values, now we can calculate the EA. So with this experiment, which is a long experiment, we have 7 different trials of the experiment. For trial 1 through 4, we are going to find the rate law. When we have the rate law, trial 5 to 7, we are going to use the rate law and calculate the K at 3 different temperatures. When we calculate the K at 3 different temperatures, then we can plot the graph. The design of the experiment, if you go through these equations, if you go or your professor with you, we go through these equation numbers 14 to 19, you will come up with the idea why we are using this equation 19 to calculate the value for rate. So that actually depends on the design of this experiment. Based on the design of this experiment, we are going to see color change when like 10% of the reactant has been consumed, and we can use that change in concentration over the time, and we have come a simplified version of calculating rate based on design of this specific reaction experiment. So this is a simplified version of calculating rate. So delta T is the time required for color change. When you see the color change, you can record that time, and that is going to be used to calculate the rate for each trial. So when we do 7 trials of the experiment, basically we are going to find 7 different times for the reactions, and then you move to calculation, how you would do the calculation. So basically the data that you are going to record that is more important for you, and you cannot do it without watching the video, is that to find the time for each trial of the experiment, and then when you have the numbers, then you can do your calculation. And the last step would be to calculate EA, which is plotting the graph and finding the slope. And based on that, you would find your slope, the EA value. So for trial 1, basically I'm going to add the A1 plus a B1. So adding A1, that means my flask 1 is going to have the solutions that is indicated in this table representing A1. And then I'm going to add the B1. When I'm adding the B1, I'm using this table. So I want to make sure you know how to read the procedure, how it's done. So we have a flask 1 that I call it like A1, and then my flask 2 is a B1. So when I'm mixing the two, I'm using the A1 plus B1 for trial 1. I'm using A2 plus B2 for trial 2, A3 plus B3, and so on, up to like seven try. You see, going from A1 to A2, the concentration changes for Ki, but the concentration for reactants, for E, flask B, or for Y, it stays the same. Since the concentration stays the same, then we can calculate the order of the reaction with respect to Ki. So we find the value for X for first reactant. Then we want to find the order of the reaction with respect to S2O8 to minus. So we repeat the similar experiments, similar the same evidence. This time we are changing the values for S2O8, and we keep the values for Ki constant. So we can find the order of the reaction with respect to S2O8. A5 to A7, the concentration is going to stay the same, but what is changing is the temperature. We're going to have room temperature plus 10 and plus 20. So we have 3 different temperatures of the reaction. Then if we find the value for X, value for Y, which is order with respect to reactant 1, order with respect to reactant 2, for a single reaction is not going to change at different temperature. The order is going to stay the same. The concentration, we have concentration for A and B, we have it. So when we find the time for reaction, we are using equation 19 to find the rate, and we have the equation we find the value for rate, plug into general rate law for the reaction, and we find the value for K at 3 different temperatures, which is needed for final calculation for activation energy. Part D of the experiment, it's not actually experiment, but it tells you in detail how to find the concentration first for the reactant 1 or reactant 2. Remember, flask 1 and flask 2, when you're adding together, the total volume is going to be count for the V2. So if we have the V1 and we have the M1, the V2 is the total volume, not just the flask 1. So the total volume, the way this experiment is designed, when you add A1 and A2, the total volume is going to be 19. It's not going to be 8, it's not going to be 11, it's going to be 19 because you are mixing the 2 flasks together. So when you are using your M1, V1, M2, V2, the only part that is challenging is finding the value for V2. I don't want you to assume only flask 1 or 2. So you add the 2 together, it's going to be 19 milliliters. So using this M1, V1 equals M2, V2, you can calculate the concentration of like iodide ion or the concentration for S2O8 for different trial. So just that the only challenging part was the V2, and is going to be 19 for every trial for value for V2. To find the rate for 1 to 7, trial 1 to 7, you have time, which you are going to record when I'm doing the experiment. And then you find the rate for all different trials separately using the simplified equation. This is not universal equation, but is the equation that is applied for experiment designed in this lab manual. So you're going to follow the steps in order to find the rate law, order of the reactions, and then overall order for your reaction, and you are going to find the value for EA. Okay, but my major concern today is, because you could all learn about this in lecture, you could learn about this from your professor. The part that you cannot do with not being here is to get those time values. So I'm going to follow the procedure. So I am following the procedure from the experiment 2 in order to perform experiments. For the experimental procedure, just Erlenmeyer flask, label 2 of the flask A1 and A2, and the other 2 B1 and B2. This is for part A. So I'm going to take 4 flasks, and I'm going to label them. A2, A2 here, labeled. I can use this. B1. And we are going to use the table in order to fill up each of the flask. Flask A1, 1 milliliter of starch, 2 milliliters of the S2O3, 8 milliliters of Ki. The burettes are set here. Fill it up to, adjusted at 10, so I have like straightforward numbers to work with. Let's go. So A1, I need 8 milliliters of Ki. I'm going from 11 to 19 exactly. I need 2 milliliters of S2O3. 2 milliliters of S2O3, going from 10 to 12. Uh, 1 milliliter of starch. Starch is the indicator. So the color change is going to be formation of the blue color. So I added 1 milliliter of starch to A1. A2 is going to be 1 milliliter of starch Usually students are working in groups and each one is measuring one or the other. But since I'm working by myself, I have to manage everything by myself, which is okay. Okay, I need 4 milliliters of the Ki. So I'm going from 19 to 23. Two milliliters of S2O3. 4 milliliters of KNO3. From 15 to 19. So these numbers you don't have to memorize, you don't have to record it because these numbers are following the table. So it's going from 15 to 19. It's kind of slow, so I'm just going to give it time. B1, 4 milliliters of S2O8. Have my A2 ready. For B2, going 4 milliliters of S2O8 and 4 milliliters of SO4. From 4 to 14. And I always read the label. Going from 20 to 24. So B2 is ready. B1, same way, 4 milliliters. It's going to go from 28. And here 14 to 18 of S2O. And B2. S2O8 and there's always room for error, but we just try to minimize it. So I kind of grouped the burettes that I need for B together. So I have my flasks prepared. So we are going to initiate the reaction by mixing A1, B1, and we are going to start measuring the time. And we mix it well and record the time for trial 1. So delta T for trial 1. And your data sheet is going to be on part A, trial 1. So I'm going to record the time for until color change for trial 1, time for color change for trial 2. That's how I'm going to record the numbers for you. Timer, so make sure that it's on. Start, stop, reset. Okay. I have my flasks A1 and B1 ready, A2, B2. So for trial 1 and 2, I'm going to have the record the number. So going to record mixed A1 with B1 at the same time. As soon as it mixes, as soon as the two liquids touch each other, I'm going to start the timer. And I'm waiting for the color change. When the color change takes place, if it takes place, I would stop the timer. I don't remember from last semester how long it took, so you just have to be patient. Wait until the color change takes place. Okay, 32 seconds. It took me 2 seconds to record, so 32 seconds. So I'm going to record that for you here in the chat here. Time until color change. Trial 1 equals 32 seconds. Okay. You usually do this like 3 trial of the experiment. I want to make sure it's just 1 trial. We kind of repeat the experiment 3 trials. I didn't ask in this experiment. I usually ask students to repeat this. Okay. So that was trial 1, and I'm going to do the same experiment for trial 2. So I'm going to add the, first of all, reset my timer. Mix the A2 with E2. And wait for color change. We have lower concentration of A for second trial, so it kind of makes sense for it to take longer. I'm waiting for the time for the blue color to appear. Okay, very good. So I have 64 seconds time until color change. Try 2 equals 64 seconds. Okay. We are done with 2 experiments. 2 experiments done. Now I need 4, 9, I need more. I do need more flasks. Can I please have 6 more Erlenmeyer flasks, the size 50 milliliter? Thank you. Okay, I'm going to start labeling by B3, A3, B3, A3, B3. I would definitely be more happier if you were here. You could do part of these preparation for me. So anyway, my A3, I need 1 milliliter of mix up. Starch. 2 milliliters of S2O3. 2 milliliters going from 14 to 16. 4 milliliters of KI. 23 to 27. KI. And 4 milliliters of KNO3. 20 to 24. I need 4 more liters. 20 to 20. This is kind of slow. So while it's taking time, see it's coming drop by drop. It's kind of slow. A3 is ready. A4, same thing. 1 milliliter of starch. 1 milliliter, 2 milliliters of S2O3. Going from 16 to 18. 4 milliliters of Ki and 4 milliliters of KNO3. 4 milliliters. 27 to 31. 24 to 28. 24 to 28. 24 to 28. A3 and A4 are ready. So I'm going to make the B3 and B4. B3, 4 milliliters of each. S2O3 and SO4. S2O8, 4 milliliters. And from 18 to 22. This one will be from 28 to 32. B3 is ready. And I need to make the B4, 8 milliliter of S2O8 only. 8 milliliter of S2. Going from 22 to 30. I have 8 milliliters in the flask B, 11 milliliters in flask A. When I'm mixing together, the final volume is going to be 19 milliliters. That's why you calculate concentration in the final mixture based on 19 milliliters. Okay, so I have my solutions ready. I'm going to mix A3 with B3 and record the time. And when I'm done with that, I would mix the B8, B4 and A4 together in order to record the time. So I'm going to reset my time and start with mixing A with B. I start the time. And wait for the color change to happen. As soon as the color change happens, I would stop the timer, record the time for you, and move to the next. stop the time because the color change happened. And I have 59 seconds. Going to record 59 seconds. About 59.5. Just like it shows in the data sheet, so you don't get confused with this. Is for part B, time until color change. Same thing. For trial 3 equals 60 seconds. Because of the decimal, I just rounded up to 60 seconds. Okay. Next, doing the experiment for A4 plus B4. I have to be ready to start the time as soon as it touches. And we're going to wait for the color change. It might take less time than A3. Yes. 29.8. Okay, 29.8. I can actually set for 29.8 or 30 seconds for the second. Trial 4 equals 30 seconds. Okay, done with 4 trials. Now the next one's going to be a little bit more. It requires a bit more of attention because we have to have a fixed temperature. We have to. Okay, first of all, flasks are not here, so I'm just going to go to prep room and grab the flask, and I'll be right back. Tell them I got them. I got the flask. Don't worry. Okay, label them. Even if they look clean, they must be clean and dry. Once we use them, we cannot reuse them again. Going to prepare labels. Prepare the label. I have A5. Have A A7, A5, A6, A7. We have B7, B6, and B5. Prepare the samples based on the table again. Following the table exactly. A5, 1 milliliter of starch, 2, 4, and 4. So I've had students who have to repeat experiments actually for 5 times because when you rush through getting your sample, you can make mistake in order or the quantity, and is not going to work properly, or you won't see the color change at all. You forget the starch. So that's why I'm taking some time trying to prepare my flasks properly. 2 milliliter of S2O, going from 18 to 20. 4 milliliters of Ki, 4 milliliters of 3 to 22, and this is for my snow. 6, I have my starch. 2 milliliter, 4 and 4. 5 is ready. 2 milliliter of S2O3. 4 milliliters of Ki, going from 35 to 39. 4 milliliters of KNO3 from 30 to 30. And 39 to 43. A6 is ready. And 36. I should not rush. So I'm going to make a new flask for A7. A7. One more of starch. 2 milliliters of S2O3. 4 to 26. 43 to 47. And this one from 36 to KN 36 to 2 and 6. Going to make my solutions be 2 milliliters of S2O8, 6 milliliters of SO4. Currently going down to 32. 32 going down to 38. I have the one of these ready. 2 milliliters and 6 milliliters. 2 to 34. And this one from 38 to 44. Okay. Try this ready. V5, V6, V7 ready. Now I have the solutions ready. One is at room temperature, one is 10 degrees higher, and the other one is 20 degrees higher. So I'm going to also prepare hot water bath so I can place my samples in to check the temperature. Hot water bath is getting ready, but I can do the room temperature at this point. For the room temperature, we mix the A5 plus B5, and the room temperature is okay. Thermometer shows 24.9 degrees Celsius for the room temperature. So room temperature is 24.9 degree. But this is a Celsius, and for the calculation purpose, we need to change that to Kelvin, because the value for R is using Kelvin temperature. So A5, B5, going to mix and start to mix the two. I start the timer, waiting for the blue color to appear. This is for room temperature. So using trial 1 and 2, you find the value for X. Using trial 3 and 4, you find the value for Y. Now you have the value for X and you have value for Y. Rate for all 7 of them is using equation number 19 in the lab manual for this experiment. We are trying to find the value for K, which is the rate constant at 3 different temperatures. Room temperature, of course, is going to take the longest. Coincidence or what? 120, 120 seconds. 120 seconds. Let's see. Trial 5, which is A5 plus B5 equals 120 seconds at room. Okay. A6, B6 is supposed to be at 34.9 degrees Celsius, because we are going to increase the temperature by 10 degrees. So I'm going to place A and B at the same time. I place it in the hot water, wait for the temperature to increase to 34.9 So the temperature has to go up. Temperature. I have to hold both flasks with my hand or clamp it because I don't want anything to flip and give me the wrong or spill the chemicals into hot water bath. Okay. Going to mix the two. 10 degrees higher. It should take less time. If anything goes wrong, I repeat the experiment, but it should take less time than the room temperature. Took 85 seconds. 85 seconds. 84 point something. So going to trial 6, which is A6 plus B6 equals 84 seconds at 34.9 degree. Which is a 10 degree higher than at the 10 degree higher. This is a 10 degree higher than room temperature. Let me see how your report sheet wants this data to be recorded so I don't confuse you. I want to make sure that you are second. So A5 plus B5. Okay. Should be clear. Time. Solid requires. Okay. Next one is A7 and B7. I like to clean up my workstation. I want to make sure that there is no extra flask here. I don't confuse myself. Okay, let's see. Last one. This should take much less time compared to the other two. So it should be less time compared to trial 5 and trial 6. So I'm going to look for the temperature in one of the flasks. Wait until it reaches, this time I was 35, should change to 45. So I'm holding both flasks in the hot water bath. I'm monitoring the temperature, making sure that temperature reaches 45 degrees Celsius, about 45, or 44.9. The temperature for the liquid should be that much. When it's sitting there, if the thermometer especially touches the bottom of the pan, it might record a different number. So I have to lift it up, check the temperature, make sure that it's higher than 45. Okay, now it's higher than 45. I'm going to wait until it reaches 45 for better or more accurate measurement of the temperature. So 44.9 or 45, I take either one of them, but as soon as it reaches to the 44.9, I mix the two. Okay. The temperature went below 44, so I had to put it back in the, to make it 44. It went to 44.8 actually. Okay, 36. 37. Okay, perfect. Okay, you have all the numbers, and part D of the experiment is just the calculation. I hope that you, by listening and watching the video, you can get the data you need for to fill out the data sheet and do calculation to turn in your data sheet as an assignment to professor. The only precautions I just said, I mentioned earlier, the secondary volume, the V2 value is 19. Everything else is kind of straightforward. If you follow the steps that you have for Part D for calculation, you should be able to do the calculation clearly. I showed you earlier on the screen, and now I'm holding the lab manual. This is the lab manual. You buy it from Vital Source. You have access to it, and you can follow it. Make sure you plot a graph and you draw the best fitted line before you calculate the slope. We are done with the experiment 2, which is kinetics, part 1, or the rate law and activation energy. And I hope that was helpful. And I'm going to stop the recording. Thank you.